Hey everyone, today we're going to talk about doing more stuff with the dot product, more specifically the projection of a vector onto another vector. And so the concept comes from this idea of if you were to have a, let's say for example you had a ramp and you had an object resting on the ramp. So here's your object on the ramp. Only because I can't draw anything fancy, I'm just using a block, but it could be a car parked on a ramp or something like that. And there are different forces that are acting on this body. There's this idea of the force that's pushing it down into the ground is a force. We can call that F1. And then there's this force that is wanting to pull it back down the ramp. And that force we'll call F2. And so the result of those two forces is something in the middle. And that would be your resultant force. And so that resultant force, or vector if you want to call it that, would be the sum of those other two vectors. That's a 2 there. Okay, so that's the idea of where that comes from. Okay, and we're going to talk about what this means and how we're actually going to deal with it. So if we go to this picture, here's the idea. We've got this vector u, and then we've got this vector v, and then the projection of v onto u. So basically if you drop a perpendicular right down to vector u, and where that perpendicular meets vector u, that is the projection of v onto u. Okay, so that's the idea. So what does that do for us? Well, let's go through a couple of things first. Yesterday we talked about the dot product, and we said the dot product of two vectors, right, in general, we said the dot product of v and w would be the magnitude of v times the magnitude of w times the cosine of the angle between them. Okay, and if I do a little bit of manipulation, I can divide both sides by the magnitude of w, and that's going to give me the dot product of v and w over the magnitude of w, and that's going to be equal to the magnitude of v times the cosine of theta. And you might be like, well, that's great, but I don't even know what I'm doing with that. And remember, these letters are arbitrary, right? These letters are arbitrary. The idea being, actually, you know what? Let me change this to W just to make it easier. So instead of calling that U, we'll call that W to match up with the letters I have here. Okay, so if we go back to this picture, right, we have a right triangle here. And this segment right here, this is the projection. And we're going to write it as the projection of V onto W. Okay, so I have a right triangle here. Here's my angle theta. And just by straight right triangle trig, I know that the cosine of theta is going to be the projection vector over the actual vector V, right? So I can say that the cosine of theta is going to be the magnitude of the projection of V onto W over the magnitude of V. Okay. If I were to cross multiply, I get the magnitude of V times the cosine of theta is equal to the projection of V on to W. And if you notice then, that's what I have down here, and that's what I have here. So I'm going to substitute this in for vector v cosine theta. Okay, so if I substitute that in, I end up with the dot product v and w over the magnitude of w is going to equal the magnitude of the projection of v onto w. So that is part of where our formula is going to come from. Now, we've got one more step to get what we need. So what I'm going to do is this, and again, this is not something you're going to need to memorize the derivation of this. You're just going to have to know how to use this formula. Okay, so we've got the projection of V onto W. Notice I took out those symbols for magnitude, because what's going to happen is I'm going to take what I have, which is the dot product of V and W over the magnitude of W, and I'm going to multiply it by the unit vector in the direction of W. The unit vector is this. So what we end up with for the projection, and we're going to do an example of this, is the dot product of V and W over the magnitude of W squared times W. And that is the formula for the projection of V onto W. Okay, again, not something you're going to need to derive, but you do need to know. So let me show you how that is used in an example. And here we have the whole formula up here for you, but that's just where it came from. Okay, so let me show you how we use that in an example. So we've got vector V and vector W. Find the vector projection of V onto W. So let's go ahead and graph these vectors first. I've got 2i plus 4j. So 2i plus 4j. That puts me right there. That would be vector V. Okay, and then negative 2 plus 6, that's going to be W. Right? So the projection of V onto W, right, if I were to drop a perpendicular, this right here would be that projection. That piece right there would be that projection. We're going to find it mathematically. Okay, so the projection of V onto W is going to be the dot product of V and W over the magnitude of W squared times W. Okay, so the dot product of V and W, remember we're just multiplying the horizontal components together plus the product of the horizontal components over the magnitude of W, so that's going to be negative 2 squared plus 6 squared, and then I'm going to square that, and then I'm multiplying that by W. So let's figure out what this calculation is first, and then we'll apply vector W to that. So I've got negative 4 plus 24, so that's going to be 20 over, let's see, this would be 4 plus 36, that'd be square root 40, but when I square that, that just gives me 40 times W, right? So if I simplify that, that's 1/2 vector W, and vector W is negative 2i plus 6j. And so if I simplify that, I end up with negative I plus 3j. And that's going to be the projection of V onto W. And you can kind of see that, right? Because here's negative 1 plus 3, and that's where my projection vector is. Okay, so that's the idea as to how to go about doing that. Okay, so the last thing we're going to talk about is work. And the idea behind this is there is work, and it's not necessarily work like you sitting and doing work, but it's the mathematical definition of work. Okay, so the work W done by a force F moving an object from A to B is defined by W is equal to the dot product of F and AB. Okay. So say for example you're pushing a car. Okay, you're pushing something or pulling something. That is when work happens. And oftentimes we're not going to use this form of it, but rather we're going to use, we're going to actually write out what that dot product is. So if I wrote out that dot product, that would give me the magnitude of F times the magnitude of AB times the cosine of the angle between them. Okay, so let me show you how we would use that in a problem. In this problem, a man pulls a child in a wagon along level ground by exerting a force of 50 pounds on a rope that makes an angle of 30 degrees with the horizontal. How much work is done by pulling the, I guess that should say wagon 30 meters. Okay, pulling the wagon 30 meters. Okay, so if I go back to my formula, I've got W is equal to my force, right, times my vector for moving object from A to B. So if I apply the formula, I've got the magnitude of F times the magnitude of AB times the cosine of the angle between them. So the magnitude of the force, F, is 50. I'm moving it 30 meters because from A to B, right, the distance from A to B is 30 meters. And the angle between the force and the direction that I'm pulling is 30 degrees, so that would just be cosine of 30. And if you did that in your calculator, that comes out to be 1,299 foot-pounds. Okay? And the reason I know it's foot-pounds is because the distance actually, I guess it should be meter-pounds, not foot-pounds, because my unit of measure is meters. So let me fix that. So meter-pounds. Okay? The distance I'm going is meters. The force that I'm pulling, is in pounds. This shouldn't say Newton. This should say pounds. Okay. So the force is in pounds. The distance is in meters. So my unit is meter pounds. Okay. If the distance is in feet, then it would be foot pounds. Okay. If this was in newtons, it would be meter newtons. Okay. So the unit of measure is just the combination of the distance and the force. Okay, and that's all that work really is. It's pretty straightforward. The questions that you have are going to be very straightforward, similar to this, but that's the idea behind it. All right, so that is going to wrap up everything with the dot product, and we'll see you next time. Thanks, guys.